Hello there. Final example for the application or first applications of the fundamental homomorphism theorem. The claim is that for any group, the group modulo its center is isomorphic to the group of inner automorphisms of this group. Okay, let's recall what these terms mean. Z of G is the so-called center of a group, and this consists of all elements that commute with all other elements of the group. This here is short notation using the commutator notation. If this is not familiar for you, this here is equivalent to saying that xg is the same as gx. So G commutes. The order of the multiplication with any other element is irrelevant because for all x in G, xg equals gx. This is for any group, a subgroup, and actually it's a normal subgroup. So this here makes sense. This is a group, even if G is not abelian. If G is abelian, then this is not interesting because the center of an abelian group, of course, is the whole group. Every element commutes with all the other elements. So this here is simply the trivial group. So in the case of an abelian group, there is nothing to see here. And then we remember what are the inner automorphisms. Those are these maps here, kappa sub G, which are called conjugation by G, meaning kappa sub G of x is x conjugated with G, meaning multiplied from the left by G and from the right by G inverse. This will turn out to be an extremely important map when we talk about group actions. For example, this is important in all of group theory, but especially there we are going to see these guys again. So the inner automorphisms are automorphisms, meaning bijective homomorphisms from the group to itself. This is a subset in general of the automorphism group, the inner automorphisms. Now, to prove this, we consider this map. Phi goes from G to the automorphism group and sends any element to its conjugation, to the bijective homomorphism that conjugates. I think we proved on some exercise sheet or in some video that this actually is a bijective homomorphism. If not, would be a good opportunity for you to pause the video and convince yourself that this indeed is bijective. This is not hard to see. You simply take kappa sub G inverse. This is the inverse map, and it's also not too hard to show that this is a homomorphism. So now phi itself is a homomorphism. What does that mean? That means that phi of G times H here in this group, must be the same as this here, phi of G composed with phi of H, because here in this group, composition is the group operation. So we compose the two maps. And also this is not hard to see. Again, please pause the video and fill in the details yourself. This here is simply kappa sub GH. And now you need to show that this is the same as kappa sub G composed with kappa sub H. Again, not hard to do, but you should really give it a try and do it for yourself. And then, of course, what is the image of phi? The image is by definition consists of all the inner automorphisms because they are defined as kappa sub G. So the image of phi is this. And what is the kernel? The kernel consists of all group elements such that kappa sub G is the neutral element of this group, which is just the identity. The identity from G to G is clearly a bijective homomorphism. Now, what does it mean when this here is the identity? This means that G must commute with every x, because then and only then this here will give me x, no matter what x I plug in. So when this here is true, then you can interchange G and G and G inverse cancel, and you end up with x again, meaning exactly that kappa sub G is the identity. So this is what is written here. Phi of G is kappa G by definition, and this is the identity of G if and only if G lies in the center of the group G. Again, this might have been a bit too fast. Pause the video and spell out the details again for yourself. So, by the fundamental homomorphism theorem, the claim now follows, because G modulo the kernel of phi here, which is exactly the center, is isomorphic to the image of phi, which by definition consists of all the inner automorphisms. Okay, as an application of this isomorphism, we try to find out what the inner automorphism group of S4 looks like, S4 being the symmetric group on 4 elements. Now, by this isomorphism, we know that this group is isomorphic to S4 modulo the center of S4. But now the center of S4 is trivial, consists only of the identical permutation. I am not sure if we have shown that on some exercise sheet, but I'll show you the argument in a second. So this factor group here is trivially S4, because if I factor out by the identity, simply this map here sending this coset to pi itself is an isomorphism, so dividing out the trivial group yields just the group itself. So this here ends up being S4 itself. So we see that S4 has exactly 24 different inner automorphisms. Why? Because the order of this group here, by definition meaning this is the set of all conjugations by group elements of S4. This is by this isomorphism the same as the order of S4, and we already know that this is 4 factorial or 24. So this is an elegant way to see that there are 24 different inner automorphisms of S4, namely the conjugations by any permutation in S4. Now you could do this by foot, not using the fundamental homomorphism theorem, but using this identity. This we proved definitely on some exercise sheet where we talked about Sn. Conjugating a k-cycle, x1 to xk, is easy. You simply take pi of x1 up to pi of xk. This is a new k-cycle. And then we know that we can deconstruct or factor all permutations into different disjoint cycles. So we know how to conjugate them. And then we can try to argue why every pi, every conjugation with pi, this is what happens here, this is kappa pi applied to a k-cycle, yields in the end a different map. So if pi is not equal to sigma, then this here turns out not to be equal to sigma applied as conjugation to the k-cycle. But in my opinion, this is always a bit messy to write down the disjoint cycle factorization of a permutation and then using these arguments is clearly not as elegant as simply doing it like so. Okay, now for the sake of completeness, why is the center of S4 trivial? Why does it only consist of the identical permutation? Well, suppose there is a permutation in the center of S4 that is not the identity. Here I should rather write, for example, now pi being not the identity means there is at least one number from 1 to 4 that doesn't stay on its place when pi is applied. So without loss of generality, I assume this is the number 1. So pi does not map the number 1 to itself. Might be also the number 2, 3, or 4, but for ease of notation, I assume without loss of generality that it is 1. Now, we choose another permutation in S4, which leaves 1 invariant, but which moves pi of 1, which is not 1 by assumption, to another number. Okay, clearly such a sigma exists. Yeah, I simply define sigma of 1 is 1, and sigma of this here, whatever this might be, for example 2, sigma of 2 is not 2, but for example 3. Yeah, so it's easy to construct such a permutation. And now we assume that pi lies in the center of S4, so it commutes with every element, especially with sigma. And now we have a contradiction as follows. Pi of 1 is pi of sigma of 1, because by construction sigma of 1 is 1. But now pi sigma and sigma pi are the same, so I can interchange the order here. So I end up with sigma of pi of 1, but this is by construction of sigma not pi of 1. So we end up with pi of 1 not being equal to itself, which clearly is absurd, showing that this must have been false. There cannot exist a non-trivial element in the center of S4. This, I think, is a neat little argument to see that the center of S4 is trivial. Okay, this already concludes our discussion of the fundamental homomorphism theory. In the next video, I'm going to show you the two isomorphism theorems, and then we move on to real applications of all this stuff. Of course, not yet or not at all to real-world applications, but at least to more interesting group theoretic stuff. All right, thanks for watching. See you in the next lessons, and bye-bye.